All right. Hopefully, everybody's still awake. Thank you for this opportunity. My name is Isabel Lima, and I'm a research chemist with the United States Department of Agriculture. And the topic of my presentation today is going to be surplus bagasse, optimizing conversion based on feedstock characteristics and process operating conditions. This is in collaboration with Damon Frecken and Erwin Bogner of the American Biocarbon in White Castle, Louisiana. So the presentation layout is going to go like this today. I'm going to basically discuss whether sugarcane bagasse and field residue production, are these feedstocks a problem, a disposal problem, a waste, or can we consider them to be an opportunity? And in doing that, I'm going to share with you a summary of the last 3 major studies that can help highlight whether it is a problem or an opportunity. So I'm going to focus on prior research, and specifically, I'm going to talk about a system that was added to Cora, Texas mill, and it's a biomass separation unit that removes field residue. I'm going to talk about another study that was done to look at different storage conditions for bagasse and the consequences of that. And then finally, I'll share a little bit of talking about using bagasse and leaf residue as precursors to make value-added products, and I'm going to focus on biochar. So the findings of these 3 major studies and the implications at the mill, the storage study under the various conditions, quality implications for the feedstock, and then what are the applications for biochar specifically? I'll look into 2 of them, used for heavy metal sorption and also in a greenhouse and the field setting. Moving forward with this information, hopefully we can make better decisions to what needs to be done in understanding better the feedstock conditions and the processing conditions in order for that question on top to go on the right side. So basically not a problem, but an opportunity. So I always put this slide up just so everybody has an idea that yes, we are producing sucrose, but there's a whole bunch of other things that are being produced along the way that we should capitalize value for. So specifically, the largest amounts produced as byproducts of sucrose production is fibrous bagasse, and that's produced at the mill. And in the field, we produce field leaf residue. It's also called trash, but I'd rather call it field leaf residue. Those are the largest byproducts by far. Bagasse, as you all know, is a primary fuel source to generate steam and electricity at the mill, but it's very variable. Its composition changes. It changes with the season. It changes with the environmental conditions. It changes with the type of extraction at the mill, and also with the sugarcane variety. When it comes to field trash, there's an estimated 4 to 5 million tons of bagasse produced in Louisiana. And we have an estimate about 15 to 20% of it available for other uses. It's not used. And then when it comes to field trash, we have about 6 tons an acre of leaf residue. But this morning after hearing Herman talk, maybe I'm thinking that I'm underestimating the production of the leaf trash. And that's about 2.5 million tons total for the Louisiana production of field trash. It is burned in the field either before, if we burn the cane before harvest, or it's burned after what's left in the field. But this practice is becoming less prevalent. Application is determined by the physical properties. So we need to understand what the physical properties of these 2 feedstocks. There's issues of moisture, ash content, carbon content, and also fiber content. In the past, these 2 products have been used or tried to be used as an animal feed, mulch. They've been used as fuel. They've been used as precursors to make some types of chemicals. They've also been used as precursors for biochar, particle board, and 2nd-generation biofuels. So in case of the bagasse, we store it. We haven't been able to use it effectively. So what happens with prolonged storage? There's microbial decomposition, and that leads to loss of fuel value because microbes are basically eating away at the carbon compounds and decreasing the fuel. All right, so as I was mentioning, and I think I paused probably around halfway through this slide. So prolonged storage of sugarcane bagasse because of microbial decomposition, we have a loss of fuel value. The microbes, those carbon compounds in the bagasse and basically losing fuel value that way. There's also spontaneous combustion that can happen with piles of bagasse. And it's also very costly to the mills. They have to be managed and the piles have to be moved around. And it's a loss of potential land for growing more sugarcane. And there's also associated environmental and health risks with it due to water runoff and off odors. So when it comes to field residue removal, there was a 2012 study done by Dr. Gillian Eggleston looking at a study on the effect of the field residue level at the mill. As we all know, field residue can be removed 4 ways. You can either remove it manually by labor, you can burn it in the field, you can change your combine harvester rate of blowing the trash out or keeping it with the billets, or you can remove it at the factory. So this 2012 study found that processing and quality parameters got worse with increased trash levels. Then fast forward to 2016, a mechanical detrasher system, which is called a biomass separation unit, was established at Cora, Texas, and a study ensued to determine the effects of removing leaf trash by using that mechanism. So in addition to biomass generation, so basically what we're doing with segregating that biomass and generating it as a feedstock, we can increase the mill efficiency and production, and we believe that this can improve revenue both for the mill, for the farmers, and for the landowners. So this study has been published in the International Sugar Journal and is cited down here. So this is the mechanical detrasher system. The study included 3 trials with on and off detrasher, and we also use whole stalk cane for comparison to the before and after system to know how much trash is present in the cane. So here you can see the before and the after, and we can definitely clearly see that the after billets look much cleaner than the ones before. So what we did, we took samples, various samples, and averaged them at the end. And we segregated them manually with the detrasher off and with the detrasher on. And then we weighed all the fractions. So the detrasher was able to remove the green leaves, the brown leaves, soil, roots, and also the growth point region. So with all those calculations, what did we find? We found that the detrasher removed all kinds of trash, all those. The trash variations were stabilized by the detrasher. And overall, based on the studies, there was a 34 to 53% removing of that field residue. What this means is that the grinding rate was inversely related to percent total field residue, and we observed a 3 to 4% increase in the processing rate of the billets for each 1% decrease in the total trash. So this means that if you take into account the whole season, and if you have a 7.2% trash in your billets instead of the 18%, you could see a reduction in 5.1 days in the processing season, which is significant. And you see this results down here. Changing gears now, looking at the sugarcane bagasse storage. So during storage, sugarcane bagasse quality, as we know, is affected by the sugarcane variety, by the environmental and seasonal conditions, processing conditions at the mill, the way you harvest the sugarcane, and also the depth in that pile. The stored bagasse was collected monthly up to 9 months from 3 factory piles. So the difference between the storage was some of the piles were covered, some were uncovered, and one of the piles was uncovered, but was bagasse that went through diffusion instead of milling, and that was from Enterprise. So here are the results. We looked at proximate analysis, and we see moisture content, ash content, fixed carbon, volatile content, the total carbon content, and finally, fuel values were estimated empirically from the values from the proximate analysis. One we can see is that when you have covered bagasse, the ash content doesn't change much. It goes up, but it's much lower than that from uncovered bagasse. The same thing happens with the carbon content. The carbon content was around 45%, and it went down slightly through storage, which is expected. But when you compare covered with uncovered, the carbon content goes down significantly for the uncovered bagasse, whether it's diffused or milled. And finally, the fixed carbon also correspondingly goes down when we have an uncovered bagasse situation versus covered. And ultimately, if you look at the high heating value and the low heating value, those get significantly reduced from having the bagasse uncovered versus covered. So we have to be mindful of this when storing our bagasse and wanting to use it as a fuel. And specifically, the case when we have the mills that need to use bagasse that was priorly stored from last year to start up the mill at the beginning of the harvesting season. So here, as you can see on the top, we have higher heating value that does not take into account moisture. Lower heating value is lower because defective moisture. And in those little numbers, you see that moisture significantly affects the lower heating value. And in addition, the storage conditions, when we have uncovered storage, we have lower and higher heating values versus the covered mode. Here, we also see that in looking at the mineral content of that bagasse, that increases during storage. So we looked at phosphorus, magnesium, calcium, potassium, and we saw that all these minerals go up with storage. So they basically get concentrated. So we saw also a higher microbial load variability with the storage outside, not covered. And the results are consistent with the events of temperature and precipitation fluctuation during storage. So, so if we want to look into this, we would think that maybe forced drying before storage, if we special stack, if we pile the cover, if we pile cover and densify processes, we can improve the storage, the handling, and the transportation and future conversion. Switching gears again, we're looking at biochar as a sorbent for heavy metals. So what I decided is that both bagasse and field residue are two excellent feedstocks to make biochar. So initially, I was looking at biochar as a remediating agent because my previous research had shown that that was the case. So what I did is that I grabbed field residue and bagasse and carried out this study looking into the fact that the feed source in pyrolysis conditions on properties of sugarcane bagasse biochar. So we produced biochars from bagasse, fresh and aged bagasse. Again, it's important because we have both available, and leaf residue. We looked at the pyrolysis conditions from 350 to 800 degrees Celsius and residence time of 1 hour. And then we characterized and tested the biochars as sorbents for remediating heavy metals, and we looked at copper, cadmium, and lead. This is our little furnace in our laboratory, and we produced these two biochars here on the right. And we did different analysis. We looked at proximate analysis, we looked at surface area of the biochars, and we exposed them to the heavy metals, and we did isotherms to look at adsorption. So what we found in a summary was that ash content of the biochars goes up with pyrolysis temperature as expected, and that depends on the feedstock. And here we have FB, fresh bagasse, FR, the field residue, and AB is the aged bagasse. Volatile content goes down with pyrolysis temperature, obviously, because those volatiles are volatilized during pyrolysis, the higher the temperature. And then the fixed carbon concomitantly goes up with pyrolysis temperature. And that happens more with fresh bagasse than the other two. So there's definitely pyrolysis conditions and feedstock type that generates biochars of different properties. Here on the bottom, when we activated our biochar, which we increased the porosity by doing that, we also noticed the improvements. So from fresh bagasse, well, we saw that the absorption of here at copper for biochars produced at 650 was relatively low, but when we used leaf residue or aged bagasse, we saw much better results We also saw better results when we activated a biochar. So again, pyrolysis conditions and then the type of feedstock had an impact for the quality of the biochar. Shifting gears again, we looked at biochar soil amending, and we did two major studies. One was a greenhouse study with good results, and then we followed through with a soil amendment study. So for those who are familiar with biochar, it is generally known that biochar enhances soil health. It improves the water holding capacity of the soil. It increases definitely the soil carbon, aeration and drainage. It increases retention of nutrients, decreases fertilizer runoff, and in general improves crop yield and as it provides to nutrients to the crop. Here is our experiment. We did 60 treatments at 2 application rates of biochar. We had 2 biochars made from bagasse and leaf residue. We also had controls without treatment, 4 reps for each treatment, and we did single and combined treatments. Here on the right, you see why biochars are so unique, specifically from bagasse and field residue, because there's that structure, there's cell structure present for the native material, and the porosity that allows for these biochars to hold on to the nutrients in the soil. So overall trends we saw, we did a 40-year study, plant cane all the way through 3rd stubble, and then we looked at sugar yield, so pounds per acre. So we have the control, which is no treatment, and then we had the various treatments. And we have the sugar yield again, and then the average per treatment. This is over all treatments that had either biochar from leaf residue at 1 or level 2, or combinations thereof. So in general, all the treatments had better results than the control. So here you see 9,876 pounds per acre for the control, where we had an average of treatment of 10,192. What we observed and what we would expect is the control would go down over the 1st stubble, 2nd stubble, and 3rd stubble, which happened. But what we observe is for all the treatments that had biochar, that didn't happen. Instead of going down, it slightly went up year after year. So if we look at the percent increase from control, we see that the differences get better and better as we progress from plant cane all the way to 3rd stubble. If we look here at the middle, and we looked at leaf residue at level 1 or level 2 and bagasse at level 1 or level 2, we measured millable stalks, sugarcane yield, TRS, and sugar yield again. And then what we see is that this is means of 4 harvest years. So we see that leaf residue biochar application led to increased stalk count, the cane yield, and sugar yield. And these are the numbers that it increased by on average per acre. So finally, on the bottom, what we did was we added the cumulative sugarcane and sugar yield over the 4 crop years that we looked at. And then if you take into account an estimated price of domestic sugar of 22 cents a pound, and you can calculate the yield, the sugar yield per acre, then you can put a dollar value to this based on the increased sugar yield, right? So we observed that over the 4 years, you have a profit of 2,452 that has to do with the sugar yield from that treatment for leaf residue at level 1, 2, bagasse at level 1 and 2. So these were encouraging results, and we're continuing on with these studies, doing a more commercial large study in a field where the biochar is spread over several acres. All right, so based on this information from these studies, we now understand better the properties of the bagasse and the field residue and the possibilities that there are. So we're looking at these 2 feedstocks as multifaceted opportunities rather than a waste. That's the important part. There's also new incentives for coal to biomass conversion for fuel applications, and a steady growth of the biomass power market to meet demand for the green energy. And that happens all over the world now. There's new applications and emerging markets for pelleted bagasse and biochar. So the objectives moving forward will be to understand the feedstock composition variability and implications for the final product characteristics. So we want to evaluate the best processing conditions for conversion of aged bagasse, fresh bagasse, and leaf field residue into white pellets and biochar, understanding that these 3 feedstocks have very different characteristics. So I did some research recently, and I looked at these streams. I looked at fresh bagasse and aged bagasse from the pile. And what happens is that when you mill and segregate or screen the bagasse into different particle size fractions, what happens is that the smallest particle size fraction is the one that has the highest ash content. So in doing that, if your initial bagasse ash content is higher, and if you screen it and sieve it, what happens is that you look at the different mash sizes, 16, 30, 50, and 70, and then smaller than 70, and this is the opening sizes for the mash. You see that the ash content increases as you go down in particle size, right? And you also see significant differences between fresh bagasse and aged bagasse. Fresh bagasse has much less ash content, where aged bagasse has much higher ash content. And then again, you see much higher ash content for the lower particle size distribution portions. When it comes to fixed carbon, you also do the same. You see that fixed carbon content is higher for the larger particle sizes and lower for the smaller particle sizes, specifically the lower than 70 mesh. And it's higher for the fresh bagasse and lower for the aged bagasse. When it comes to moisture content, also it's very important. Moisture content for these feedstocks varies incredibly. The aged bagasse is out in the elements when it rains a lot. Moisture content increases, and it also increases when you have aged bagasse. So in this current and further studies, the conversion efficacy is feedstock dependent. So we have high moisture to deal with, we have decomposition, and we have variability. Even within the pile of bagasse outside, there's differences between the top 2 feet, the middle, and the bottom. Things happen differently because of microbial degradation steps that are different depending on access to oxygen in that pile. So looking at proximate analysis will be a good tool to understand the differences between these two feedstocks. So when we partition the feedstock, as I mentioned, into streams with different properties by milling and screening, then we can segregate sections of that bagasse that are high ash versus sections of that bagasse that are low ash. So ultimately, what we want to do is we want to produce high density, high quality bagasse pellets for the fuel market. Those have very specific characteristics and demands. The Pellet Fuels Institute specifies specifically bulk density of the pellets has to be between 38 and 48 pounds per cubic feet. The pellet degradability has to be higher than 95%. This is the stability of the pellets if they degrade into fines. Ash content has to be lower than 6%, and moisture content has to be lower than 10%. So based on these characteristics, we understand how we have to segregate that bagasse to have a fraction of that can meet that market. And when we look at low density bagasse pellets for specialty applications, we also can do that. So that would be the smallest particle size bagasse. And we can also get these from the pelletizer dye. The pelletizer dye has a life in itself. When it's over, it's degraded, it's eroded by the use. And we can use those pellet dyes that are no longer good for the high quality pellet market to use it for the low quality pellet market. And that pellet won't be used for the heating market, but it might be used for markets such as adsorption and other types of applications. Ultimately, also, we want to use those fractions that are higher in ash for the production of biochar. We decided that biochar actually benefits from having a higher ash content because of the functional properties of that biochar. So we can use leaf, field residue, and aged bagasse to produce that biochar. And that's the high ash fraction from the screening of the bagasse. Ultimately, when you also make biochar, you can use the syngas produced from the pyrolysis system to supply heat for the whole system. So I'll leave you with those thoughts, and thank you for your time. And I'm sorry again for the connectivity problems, and I'll entertain any questions you might have.